9.7 Lesson 1, Taylor Polynomials and Approximations. We have 3 objectives for today's lesson. 1, you'll be able to find a first-degree polynomial function p sub 1 to approximate a given function f at x is equal to c. And we will use that example to develop our understanding for objective 2. And that will lead to the definitions of nth Taylor polynomial and nth Maclaurin polynomial. And then we will use that definition to find an nth degree Maclaurin polynomial for a given function f for objective 3. So our vocabulary for today is nth Taylor polynomial and nth Maclaurin polynomial. So let's take a look at objective 1. You'll be able to find a first degree polynomial function p sub 1 to approximate some function f at x is equal to c. So in my example, our function that we want to approximate will be e to the x. And you know about the graph of e to the x. You can sketch the graph of f of x is equal to e to the x, and it will look like this. Now, if you don't remember, you can make a quick table of values. So e to the 0 is 1, e to the first is e, and e is approximately 2.7. So that gives you these 2 points that are on your graph, and you have other points. There is a horizontal asymptote as x goes to negative infinity, y goes to 0, and then the graph shoots to infinity as x goes to infinity. So that's the graph of f of x is equal to e to the x. So in objective 1, we want to be able to find a first degree polynomial function as an approximation for f of x is equal to e to the x at some value c. So we're going to say approximate this function at a particular chosen value c, which we will choose to be 0 for our example. So what that means is, at this point where x is equal to 0, we'd like to center our approximation. So conceptually, this is what we're going to do. We're going to find the equation of a line, because we're going to be finding a first degree or a linear function to approximate f of x is equal to e to the x. So what we will do is we're going to find the equation of the line that is tangent to the graph of f of x is equal to e to the x at x is equal to 0. And we're going to say this tangent line is our approximation for the function f of x is equal to e to the x. And why is it an approximation for it? Because its values for the gray line are pretty close to the output values of the function f of x is equal to e to the x, as long as the input values are pretty close to 0. So how do we get the equation for the tangent line approximating the function f of x is equal to e to the x at x is equal to 0? Our linear function can be written generally as I've done here. A naught, which is the constant term, plus a sub 1 times x. A sub 1 is the coefficient of the first degree term. So we have a first degree or a linear function to approximate f of x is equal to e to the x, centered at x is equal to 0. So as you can see from the graph, one requirement that we have is that both functions will pass through this point, or the point of tangency. So they must have one point in common. And the other requirement is that, if you remember from calculus AB about tangent lines, the slope of the tangent line to a graph at a particular x value is equal to the slope of the graph at that x value. And what tells you the slope of a particular function's graph? The derivative. So the derivative of e to the x is e to the x. And this will give us the slope of the graph of e to the x at any x value. Specifically, we're interested in at x is equal to 0. So what will give us the slope of our linear function? You may remember y is equal to mx plus b. This is, of course, the slope. This linear function is in the form y is equal to mx plus b. It would be like b plus mx, the way it's written over here. But another way you can see that a sub 1 would be the slope of the gray line is by, again, taking the derivative of our polynomial function p sub 1 of x. So the derivative would be p sub 1 prime of x. What you have here is a constant term. The derivative of a constant term is 0, so you don't need to write that anymore. And here you have a linear term. The derivative of this linear term is a sub 1. So what we need to do is this. We've got to make sure that the linear function will pass through the point of tangency. So the two graphs must have a common point. So we'll have f of 0 is equal to e to the 0, and e to the 0 is 1. So we have f of 0 is equal to 1. And we will have p sub 1 of 0. P sub 1 of 0 would be substitute 0 for x, and you'll have a naught plus a sub 1 times 0, which is 0. So what we have is p sub 1 of 0 is equal to a naught, and f of 0 is equal to 1. And since we want the two functions to be equal to each other at x is equal to 0, that means a naught has to be equal to 1. So we now know that in p sub 1 of x, a naught will be equal to 1. So we write 1 plus a sub 1x. So we still have to figure out what a sub 1 should be to get our equation for the gray line. So to make that happen, what do we need to do? We want the gray line to have the same slope as the graph of f at x is equal to 0. So what is the slope of the graph of f at x is equal to 0? We look at the derivative, and we evaluate the derivative at x is equal to 0. So we have e to the 0, which is 1. So what is the slope of the line at x is equal to 0? Again, what do you look at? You can look at the derivative. The derivative of this linear function at any x is the constant a sub 1. So you're going to just set f prime of 0 equal to p sub 1 prime evaluated at 0. So that's going to be 1 is equal to a sub 1. So a sub 1 is equal to 1. So we have p sub 1 of x is equal to 1 plus 1x. What you see on this screen is the graph of f of x is equal to e to the x, and the graph of the first degree polynomial approximation for f of x is equal to e to the x, centered at x is equal to 0. And you can see that the blue line does a pretty good job of approximating the function f of x is equal to e to the x for x values that are close to the center that we chose, x is equal to 0. So the next question that we have is, what if we want another polynomial function that will do a better job of approximating f of x is equal to e to the x at x is equal to 0 compared to our linear function? So the next degree higher than a linear function would be a quadratic function. So we would now like to consider how we can come up with a quadratic function that would approximate f of x is equal to e to the x at x is equal to 0. And we're going to follow a process similar to how we came up with our equation for the linear function. So now we start our work trying to approximate the function f of x is equal to e to the x with a second degree polynomial function. And we'd like to center our approximation at x is equal to 0. So when we tried to do this with a first degree polynomial function, we had two requirements: that the first degree polynomial function and the function f share a common point of tangency, and that the two functions have the same slope at x is equal to 0. And And mathematically, what that came out to was just requiring that the function evaluated at 0 and the polynomial function evaluated at 0 would be equal to each other. And the first derivative of the function evaluated at 0 and the first derivative of the polynomial function evaluated at 0 would be equal to each other. So if we wanted to continue that process and follow that logic, for a second degree polynomial function, we'd like that the second derivative of our function evaluated at 0 should be equal to the second derivative of our polynomial function evaluated at 0. And graphically, you can think of this as requiring that the concavity of the original function's graph at x is equal to 0 should be the same as the concavity of the approximating polynomial function's graph at x is equal to 0. In other words, if one is concave up at x is equal to 0, the other should be concave up at x is equal to 0 as well. So that's how you can think of it geometrically. But mathematically, we're just going to require that the function f of x is equal to e to the x evaluated at 0, and its first two derivatives evaluated at 0 will be equal to our second degree polynomial function evaluated at 0, and its first derivative and its second derivatives evaluated at 0. So that tells us that a naught should be equal to 1. But we still have to find a sub 1 and a sub 2 to get our quadratic function. So we're going to do exactly what we just said before. Now we're going to find the first derivative of our function, which would be f prime of x. We're using e to the x because the derivatives of e to the x are just e to the x. It makes our work easier to do. And then the derivative of our second degree polynomial function can be found easily. The derivative of the constant term a naught is 0. The derivative of a sub 1 times x is going to be a sub 1. And the derivative of a sub 2 times x squared would be 2 a sub 2 x. So again, what is it that we want? We want to set the derivative of our function f evaluated at 0 equal to the derivative of our second degree polynomial function evaluated at 0. And when you evaluate the derivative of the second degree polynomial function at 0, you just substitute 0 for x here, so that gives you just a sub 1. So you want f prime of 0 to be equal to p sub 2 prime of 0. So you want 1 to be equal to a sub 1. So that tells you that a sub 1 should be 1. So now we know a sub 1 as well. So we have two of the coefficients that we want. We've got a naught and we've got a sub 1. So how do we find a sub 2? As we said earlier, now we're going to find the second derivative of the function e to the x. And we're going to find the second derivative of our second degree polynomial function. So you take the derivative of the first derivative. The first derivative is here, of course. So the derivative of the constant term is 0, and the derivative of the linear term would be 2 times a sub 2. So what do we do now? We're going to set the second derivative of the function evaluated at 0 equal to the second derivative of our second degree polynomial function evaluated at 0. And notice that there's no x here. 2a sub 2 is constant with respect to x. So it would just be 2 times a sub 2. And what you're going to do now is, again, we're going to require that the second derivative of our function evaluated at 0 be equal to the second derivative of our second degree polynomial function evaluated at 0. So that gives us 1 is equal to 2 times a sub 2. And if you solve for the constant a sub 2, which is what we're after, so we can write our second degree polynomial function, you will solve for it by dividing both sides of this equation by 2, and that gives you that a sub 2 is equal to 1 over 2. So now we have everything that we need to write our function for the second degree polynomial approximating e to the x. So we're going to do that right here. So I'm just going to erase a little bit so I can go ahead and write it here. So having found that a naught is equal to 1, I can write p sub 2 of x is equal to a naught is 1. Having found that a sub 1 is equal to 1, I can write a sub 1x or 1x. And having found that a sub 2 is equal to 1/2, I can write a sub 2 or 1/2 x squared. So this is my second degree polynomial function to approximate f of x is equal to e to the x at x is equal to 0. Let's go ahead and compare the graph of the second degree polynomial function to the graph of e to the x. So we already saw the graph of e to the x earlier. It's the red graph. And we saw the graph of the first degree approximation of the linear approximation for f of x is equal to e to the x centered at 0, and that's the blue graph. And right now I want you to focus on the green graph, which is a parabola. It's a second degree polynomial function. And you can see that the green graph does a better job of approximating f of x is equal to e to the x than the blue line did. It's closer to the red graph than the blue line is, and it seems to be closer to the red graph for a larger range of x values centered at 0. Will a third degree polynomial approximation for f of x is equal to e to the x centered at x is equal to 0 be better than our second degree polynomial approximation for f of x is equal to e to the x centered at 0? We expect that to be the case. The question then becomes, how would we find it? We're going to go through the same steps that we did for our second degree polynomial approximation. And it might seem redundant, but you're going to start observing a pattern. And then we will generalize from that pattern, and then that will lead us to the definition of an nth degree, first Maclaurin polynomial for a function f, and then an nth degree Taylor polynomial function for a function f centered at x is equal to c. So here we have f of x is equal to e to the x, and we have a third degree polynomial function, a naught plus a sub 1x plus a sub 2x squared plus a sub 3x cubed. The derivative of f is f prime of x is equal to e to the x, and the derivative of our third degree polynomial evaluated, or the first derivative of our third degree polynomial function is, as I'm about to write here. Again, all I'm doing is I'm using the power rule to find the derivative. So now the second derivative of our function e to the x is just e to the x. And the second derivative of our third degree polynomial function would be, the derivative of a constant is 0, so I'll just have 2 times a sub 2 plus 3 times 2 times a sub 3x. And the third derivative of our function is e to the x, and here we will have the third derivative of our third degree polynomial function. It will just be, the derivative of a constant is 0, so we're just going to have 3 times 2 times 1 times a sub 3. Now you might notice that this is actually 3 factorial, and that's a pattern that we will see. So the next thing that we want to do is, as we've been saying before, we want to center our approximation at x is equal to 0. So our requirements are this, that the function evaluated at 0 be equal to the polynomial function evaluated at 0. The first derivative of the function evaluated at 0 be equal to the first derivative of the polynomial evaluated at 0. The second derivative of the function evaluated at 0 be equal to the second derivative of our polynomial function evaluated at 0. And the third derivative of our function evaluated at 0 be equal to the third derivative of our polynomial function evaluated at 0. So our function f and its derivatives evaluated at 0 are all equal to 1. So we will have 1 is equal to our third degree polynomial function evaluated at 0. If you substitute 0 for x, the only term without an x would be the constant term, so we will have a naught. So a naught is equal to 1. And if you do the same thing with the first derivative of our third degree polynomial evaluated at 0, again, the terms that have x will become 0 and the constant term will remain. And if you do that with the second derivative of the third degree polynomial function, if you evaluate that at 0, you'll just be left with the constant term. And if you look at the third derivative of the third degree polynomial function evaluated at 0, well, there is no term here that has an x in it. That's just a constant term. And that is, of course, 3 times 2 times 1, which is 3 factorial times a cubed. And the 2 here, you can also write 2 as 2 times 1. 2 times 1 would be, of course, 2 factorial. And the 1 here, there is a coefficient of 1 there. You can write that as 1 factorial. 1 factorial is 1. And there is a coefficient of 1 here as well. And you can write that as 0 factorial. 0 factorial by definition is 1. So when you solve for the coefficients of our third degree polynomial, you get a naught is equal to 1 divided by 0 factorial. A sub 1 is equal to 1 divided by 1 factorial. A sub 2 is equal to 1 divided by 2 factorial. And a sub 3 is equal to 1 divided by 3 factorial. And in fact, if you were to try to repeat this process, trying to come up with a fourth degree polynomial approximation for our function f of x is equal to e to the x centered at x is equal to 0, you will observe the same pattern. If you are trying to do that for a fourth degree term, you will find that a sub 4 would be equal to 1 over 4 factorial. And for an nth degree term, you will find that it is a sub n is equal to 1 over n factorial. And this is for the function f of x is equal to e to the x centered at x is equal to 0. So now if you take these coefficients for a naught, a sub 1, a sub 2, and a sub 3 and write them here, you will get your third degree polynomial function, and let's look at the graph of it. And here you see the graph of our third degree polynomial function approximating f of x is equal to e to the x, centered at x is equal to 0, and it is shown by that purple curve, which I will trace now in gold, just to make it distinguished from the other curves that are already on there. And you can see that of the ones that we've done, this is the one that best approximates the graph of f of x is equal to e to the x centered at 0. And by now you probably think the higher the degree, the better the approximation, and that's a correct observation. And this is what we're studying starting today, going forward. We're studying how to approximate functions with polynomial functions of degree n. And these are called nth degree Taylor and Maclaurin polynomials. The difference between a Maclaurin polynomial and a Taylor polynomial is the center of the approximation. For the example that we did, all of our approximate polynomial functions were centered at x is equal to 0. And if that's the case, we call them either Taylor polynomials centered at c is equal to 0, or the special term would be an nth degree Maclaurin polynomial. Maclaurin means centered at 0. You could also have nth degree Taylor polynomials centered at a different value not equal to 0, and those are called nth degree Taylor polynomials centered at c. And you can also see a fourth degree Taylor polynomial or Maclaurin polynomial approximation for f of x is equal to e to the x centered at 0, and that's shown in black. And of course, the higher the degree, the better the approximation, and this is the best of them. Now that we understand the concept of a polynomial approximation for some function f at some center c, we'd like to extend our discussion and generalize from it. So that will lead us to the definitions of nth Taylor polynomial and nth Maclaurin polynomial. And once we have those definitions, we can use them to find Maclaurin polynomials of degree n or Taylor polynomials of degree n centered at x is equal to c for some function f. So again, our vocabulary is nth Taylor polynomial and nth Maclaurin polynomial. So we'll take a look at objective 2, but before we look at the definitions, we'd like to connect the discussion that we just had to the definitions that we will look at. So how do we make that connection? That's what we want to look at now. You'll see this on page 650 of your textbook, right above the definitions of nth degree Taylor polynomial and nth degree Maclaurin polynomial. I'd like to explain it so you understand where these definitions come from. And of course, it's connected to the work that we did prior to this point in the lesson. So we began with our function f of x is equal to e to the x, and we wanted to approximate it with an nth degree polynomial function centered at x is equal to 0. Well, we'd like to generalize. Instead of having f of x is equal to e to the x, we just have some function f of x. It could be e to the x, or it could be something else, maybe even sine x or cosine x, whatever f of x may be, some elementary function. We'd like to approximate it with a polynomial function. Why is that? You'll see applications later, but you can see that it's really easy for us to find derivatives of polynomial functions using the power rule or integrate polynomial functions. So some of the applications that you will see for approximating functions with polynomial functions is that you may have a function and perhaps you don't know how to differentiate it or integrate it, but you certainly know how to differentiate and integrate polynomial functions. So you might be able to approximate the definite integral of some function f of x from x is equal to a to b, even if you're not able to find an antiderivative because you don't know how. You might be able to do that by using an nth degree approximation for it, using an nth degree polynomial approximation for the function, and then integrating your nth degree polynomial function from x is equal to a to x is equal to b, and that would give you an approximation. But that's just a discussion about applications. But let's go back to what we're looking at here. So we have some function f of x, and we'd like to approximate it with an nth degree polynomial function centered at x is equal to c. So we begin by writing our nth degree polynomial function. It is centered at x is equal to c. You may remember transformations of functions from algebra. Basically, this is the parameter h, and if you have x minus h, you have a horizontal translation of the parent function's graph c units. So basically, when we have x minus c here, we're just moving the center of our approximation from x is equal to 0 to x is equal to c. So that generalizes, because now we don't have to just think about centering our approximation at x is equal to 0. It could be centered at, for example, x is equal to 1 or x is equal to -2, whatever. But we do the same thing. we're going to find derivatives of our nth degree polynomial, the first derivative, the second derivative, the third derivative, all the way to the nth derivative of our nth degree polynomial, just like we did in our example with f of x is equal to e to the x. And we're going to do the same thing. Once we have our derivatives of our nth degree polynomial, we'd like to evaluate each one of them at the center. And the center of our approximation is, of course, x is equal to c. So we'd like to evaluate each of these at x is equal to c. And then we'd like to set the values of our nth degree polynomial function evaluated at x is equal to c, as well as its derivatives evaluated at x is equal to c. We'd like to set those equal to our function f evaluated at c and its derivatives evaluated at c to solve for these constants, which are the coefficients of our nth degree polynomial function. And once we know what the coefficients are, we will know what function we should have as our nth degree polynomial approximation for f of x centered at x is equal to c. That's basically the structure that you should see when you're looking at this particular page. So now we're going to go ahead and just look at some of the details. So when you look at the derivative of p sub n, you're just using the power rule. The derivative of a constant is 0, so a naught is gone. The derivative of the linear term here will give you a sub 1. The derivative of the quadratic term here will give you 2 times a sub 2 times x minus c. The derivative of the third degree term here will give you 3 times a sub 3 times x minus c to the second. And of course, I'm using the power rule. And same thing here, I have n times a sub n times x minus c to the n minus 1. So now to find the second derivative, I'm just going to go ahead and work with the first derivative and find the derivative term by term. And to find the third derivative, I'll work with the second derivative and find the derivative term by term, and so on. And you get to the nth derivative, and this is what you have. So you may notice that the coefficient that we have here is actually n factorial. You have n times n minus 1 times n minus 2 all the way to 2 times 1. So that's n factorial. And in fact, that pattern is something that you can observe and see even in the earlier lines in our derivation here. So here's what you should see. What's multiplying a sub n? N factorial. What's multiplying a sub 3? 3 times 2 times 1, or 3 factorial. What's multiplying a sub 2? 2 times 1, or 2 factorial. And what's multiplying a sub 1? 1 times 1, or 1 factorial. And what's multiplying a sub 0? 1, which you can write as 0 factorial. That's what you should see. So when we evaluate not only p sub n at x is equal to c, but also its derivatives at x is equal to c, this is what we'll have. P sub n evaluated at x is equal to c, all of these terms will become 0, and you'd just be left with a naught. P sub 1 evaluated at x is equal to c, all of these terms will become 0, and you'd just be left with a sub 1. And p sub 2, p sub n, the second derivative of p sub n evaluated at x is equal to c, all of these terms will go to 0, and you'd just be left with 2 times a sub 2. And the nth derivative of p sub n evaluated at x is equal to c, there are no terms with x there, so you're just going to be left with this. That's what we write here for our function p sub n of x and its derivatives evaluated at x is equal to c. This is what we have. And of course, the pattern that you should see is something that I indicated earlier. This is actually 0 factorial times a naught. This is 1 factorial times a sub 1. This is 2 factorial times a sub 2. And this is n factorial times a sub n. So now you're going to set each of these equal to the function f evaluated at x is equal to c. So when we do that, this is what we have. So when you evaluate the function f, whatever it may be, in the example that we began with, it was e to the x. But when you evaluate the function f at x is equal to c, you want to set that equal to the nth degree polynomial function evaluated at x is equal to c. So this is what you want to do. You're setting these equal to each other. Why? We saw this with our example involving f of x is equal to e to the x. And we're doing it for that reason. And when you do that and you solve for what we're interested in, what we really want are these coefficients. So you set those equal to each other and you're solving for these coefficients. So what you need to do is basically isolate these coefficients, and doing that results in the following. These are the values of the coefficients. So basically, whatever function you're trying to approximate, you will evaluate the function at c and its first n derivatives at c. And for the function evaluated at c, you will divide by 0 factorial, which is 1. For the first derivative of the function evaluated at c, you will divide by 1 factorial, which is 1. For the second derivative of the function evaluated at c, you will divide by 2 factorial. For the nth derivative of the function evaluated at c, you will divide by n factorial. That leads us to the definitions of nth Taylor polynomial and nth Maclaurin polynomial. If f has n derivatives at x is equal to c, then this polynomial, p sub n of x, and what was p sub n of x in our derivation? It was a naught plus a sub 1 times x minus c to the first plus a sub 2 times x minus c to the second, and so on until you get to a sub n times x minus c to the n. And the derivation that we did, we found what these coefficients should be. And they are right here. And where are they in the definition? Right there. So now you understand where this definition comes from. You have to go back to the example that we began the lesson with. F of x is equal to e to the x. And that idea is extended to the general case where we're trying to come up with an nth degree polynomial approximation for some function f centered at x is equal to c. And the work that we did shows that for such an nth degree polynomial function, these are the coefficients that you should have for the individual terms. And that is called an nth degree Taylor polynomial for some function f centered at x is equal to c. And if c is equal to 0, then we say we have an nth degree Maclaurin polynomial function for f, where the center is at x is equal to 0. And the only difference between these is that in the second case, which is what we're looking at now, where we just replace c with 0. We will now conclude our lesson by looking at Objective 3. You'll be able to find the Maclaurin polynomial of degree n for a given function f. So a Maclaurin polynomial is a Taylor polynomial centered at c is equal to 0. A Taylor polynomial could be centered at 0 or some other value, but a Maclaurin polynomial is always centered at 0. So we're going to use the definitions that we just derived to do our example problem. So find the Maclaurin polynomial. That means our center is at 0, so c is equal to 0, of degree n, and in our example we want a fourth degree Maclaurin polynomial for the function f of x is equal to e to the x. So what do we need to do? We need to look at the definition here of an nth degree Taylor polynomial centered at c. And c for us will be 0 because we have a Maclaurin polynomial. And all we need to do is basically to get our fourth degree polynomial function, we have to find the derivatives of our function all the way to the fourth derivative, and then evaluate our function and its first four derivatives at c is equal to 0, and divide by the necessary factorial expression to form the coefficients of our fourth degree polynomial approximation for f of x is equal to e to the x centered at 0. So to find the first derivative of f of x, I have to use the chain rule. I have a composition of two functions where the inside function is 3x. So I have the derivative of e to the 3x, which is e to the 3x, multiplied by the derivative of the inside function, which gives me 3. And then I have f double prime of x. So I would take the derivative of f prime, and I'd get e to the 3x. And then here I'll have 3 squared, which is 9. And then I'll have f triple prime of x, which would be 3 cubed times e to the 3x. And of course, the fourth derivative of the function evaluated at x would be 3 to the fourth times e to the 3x. So what we must do now is evaluate our function and each of its derivatives at our c value of 0, and then divide by the appropriate factorial expression to form the coefficients in our fourth degree Maclaurin polynomial approximation for f of x. So f of 0 is e to the 0, which is 1. F prime of 0 would be 3 times e to the 3 times 0, which is 0. 3 times e to the 0 is 3 times 1, which is 3. F double prime of 0 would be 3 squared times e to the 3 times 0, which is 0. E to the 0 is 1, so that's 3 squared. And then I have f triple prime evaluated at 0, which would be 3 to the third. And I have the fourth derivative of f evaluated at 0, which would be 3 to the fourth. Having done that, I am now ready to go ahead and write my Maclaurin polynomial of degree 4 for our function f of x. So now we're ready to complete the problem. So the fourth degree Maclaurin polynomial approximation for f of x would be f of 0, which is of course 1, plus f prime of 0, which is 3, times x, plus f double prime of 0 over 2 factorial. F double prime of 0 is 3 squared, which is 9, over 2 factorial times x squared. And I can keep this as 3 squared if I'd like to sort of have the pattern be apparent. And here I can write 3 cubed over 3 factorial times x cubed. And here I will write 3 to the fourth, which is of course the fourth derivative of f evaluated at x is equal to 0, divided by 4 factorial from the definition times x to the fourth. And that is the fourth degree Maclaurin polynomial for the function f of x. If you would like to, you can graph f of x is equal to e to the 3x, and you can graph this fourth degree polynomial function, and you will observe that this fourth degree polynomial function is a good approximation for the function f for x values near the center, which is x is equal to 0. We began the lesson today by looking at a specific example where we were trying to approximate the function f of x is equal to e to the x centered at x is equal to 0 with various degrees of polynomial functions. And then we extended our work and generalized it, and that led to the definitions of nth degree Taylor polynomial and nth degree Maclaurin polynomial for a function f centered at x is equal to c for a Taylor polynomial and x is equal to 0 for a Maclaurin polynomial. And then we looked at a particular example in which we use these definitions, especially the definition of an nth degree Maclaurin polynomial for a function f, to find a Maclaurin polynomial of degree 4 for a given function f. And vocabulary in our lesson was nth Taylor polynomial and nth Maclaurin polynomial.